All right. So this is the start of section 4.2. So what this is talking about is essentially its division. We're going to take polynomials and we're going to divide them. They've just like really overcomplicated things here. All they're saying is if we do division of some polynomial p of x and we divide it by, we're dividing f of x. Dividing it by p of x. We're going to wind up with a quotient. We're calling that q. And we may wind up with a remainder. So like if we do this long division style and it goes several lines down, we'll wind up with a remainder that we're going to call r of x. That's all it's saying, is we're going to have our quotient, our remainder, what we divided and what we divided by. That is what this statement is trying to say without having to draw a picture. And that r of x, our remainder, will have a degree of 0, or it's going to be less than the degree of our function. And what we divided by. And so we're going to do this today, and we're going to practice. We're going to start with long division. And then I'll remind you about what synthetic is. But we're going to start with doing long division with our polynomials, which you have done before. We spent a long time doing this in algebra, at least a week in algebra. So I've got a couple of people writing, so I'm going to leave this here for a second. Oops, sorry. That was not the button I meant. Okay. I'm going to change it. So here's our first piece. We're going to find the quotient and remainder if f of x is divided by p of x. And then I'll show you how we can do a check as well. So I'm going to set this up as a long division. So I'm going to build my little house. And we're going to take our f of x, our 9x plus 4, and we're going to divide it by our p of x. That's what our instructions said. Our 2x minus 5. Then what we need to figure out is we need to figure out how many times 2x goes into 9x. We could do it as a 4. That would give us a whole number. I want us to go in exactly as many times as it can go in. You can do it as a decimal, 4.5. I want to do it as a fraction. Does that mean like that? I'm going to use 9/2. It is 4.5, but that'll put it in the exact right number of times. So I would like to have as little remainder as possible. We can work with fractions, we can work with decimals. We don't have to only work with integers. So then what I'm going to do is I'm going to take that 9/2 and multiply it by this whole term down here. 9/2 times 2x gives us 9x. And 9/2 times minus 5 9 times 5 is 45/2. 9 times 5 is 45. And then what we do is we subtract our two lines from each other. Make sure we're subtracting the whole line, so just be careful with that. 9x minus 9x gives us 0 x's. And 4 minus negative 45/2 So 4 in terms of halves, that'd be 8/2 minus negative 45/2. So 8 plus 45, 53/2. So our quotient our q of x, which is another way you can write that, just because quotient's a long word, is what's on top, that 9/2. Thanks, Brian. Our remainder is this guy down here, what's left over, our 53/2. So ideally we want to wind up with our remainder having a smaller degree than our divisor, what we divided by. So that's why we wanted to make sure to use that fraction there. We need to make sure we get at least one x to cancel out. So our remainder, we can also call our r of x, just because that's the easier way to write it. So our f of x, our p of x, and our q of x. And if you want to double check yourself, the way we can do that is we actually use that equation that was in the middle of our definition, where we have f of x equals q of x times p of x plus r of x. So you could take our 9/2, our quotient, times our p of x, our 2x minus 5, and add our remainder, that 53/2. And you should get exactly what our f of x was, 9x plus 4. And you could simplify this right-hand side to double check that it works. So if you're not sure if you've done it right, this is a great way to double check. Because when we do this and we include that distribution, it should wind up exactly at 9x plus 4, and in this case it will. And it's a great way to kind of double check if we're not super confident in it. But since we need our remainder to have a smaller degree than our divisor, we have to make sure that first x cancels out. So sometimes we will wind up with fractions as our or in our quotient. It's not going to be super common, but it can happen. We're going to try this again, but questions on the first one? Okay. More often than not, we're going to have bigger polynomials than this. We're very rarely going to divide linear functions quite like this. More often than not, we're going to get polynomials like this. So here we have our f of x is 2x to the 4th minus x cubed minus 3x squared plus 7x minus 12. And our p of x is x squared minus 3. Blink. So we're going to set this up again as long division. So I'm going to build my house. Inside, I'm going to put my f of x, my 2x to the 4th minus x cubed minus 3x squared plus 7x minus 12. And we're dividing it by our p of x, x squared minus 3. All right, so what do I need to multiply this first term by in order for it to eliminate the entirety of 2x to the 4th out? 2x squared. We're going to have our 2x squared up here. Then I'm going to take that and multiply it by the whole term over here. So 2x squared times x squared gives us 2x to the 4th. And 2x squared times minus 3 gives us minus 6x squared. And I'm going to skip and put it over here so it lines up with the x squareds. Because now I need to come through and I need to subtract these down into my next line. What's up? Because we didn't actually have an x cubed in here, I wanted my x squareds to line up so that when I subtract, I actually can subtract them. So if I had an x cubed term, I'd put it under here, but I don't have one, so I don't have anything to subtract from this guy. So when we do this subtraction, what is 2x to the 4th minus 2x to the 4th? 0x to the 4th, they cancel out. That's the whole point. That first term always needs to cancel out. Our minus x cubed doesn't have anything to subtract from it, so it just drops on down. I have negative 3x squared minus negative 6x squared. Positive 3x squared. Because we are subtracting negative 6. That is honestly the most common place we lose this. We got to remember we are subtracting, so we wind up with a double negative situation here. My plus 7x and my minus 12 just drop down. And that completes round 1 of division. Long division is long. So round 2, we go back and start from the beginning. I want to know what I need to multiply x squared by to get negative x cubed to cancel out.
I found this on the
Not web. You. X, but also negative. I want it to match exactly so that when we subtract it, it eliminates out. So minus x times x squared gives us minus x cubed. What's up? I'm hearing lots of questions being whispered, but I can't actually hear them. Okay. Then we're going to have our minus x times our minus 3, and that's going to give us plus 3x. And I'm putting it way over here so it lines up with my x's. Then we're going to subtract the whole line. Minus x cubed minus x cubed gives me 0x cubes. They cancel out. That's the whole point. That first term needs to cancel out. What's up? what? Uh-huh. Negative 3x squared minus negative. It's this double negative situation, minus negative. That becomes minus 3x squared plus 6x squared. Minus negative. It becomes a positive 3x squared because of that double negative situation. Just like down here, we have our minus x cubed minus negative x cubed. That becomes minus x cubed plus x cubed, which gives us our 0. That double negative situation is where we have the most sticking points. I wonder if we're going to have a tool to help us with that here in a minute. So then when we're doing our simplification down here, my minus x cubed minus x cubed gives me 0x cubes. Then we've got our 3x squared coming down. I've got my 7x minus 3x giving us positive 4x minus 12. Round 2 done. One more round. Because our remainder has to have a degree less than what we divided by. We're not done yet. So what do we need to multiply our x squared by to get this term to cancel out? 3. So we're going to use a positive 3. Positive 3 gives me 3x squared. Positive 3 times negative 3 gives me minus 9. And we're going to subtract our 2 lines. And I am right at the bottom edge, but I can do it. Subtracting the whole line. Make sure we're paying attention to that because that messes with our signs. Our 3x squared minus 3x squared gives me 0x squared. So that term cancels out. That's the point. We have 4x. What do we get? Minus 3. Negative 12 minus negative 9. Negative 12 plus 9. 4x minus 3 is our remainder. So our q of x, our quotient, is the what's on top. When they ask you to find q of x, that's what they mean. What we wound up with on top, our 2x squared minus x plus 3. Our r of x, our remainder, is what's left on the bottom. Our 4x minus 3. Our remainder always needs to have a smaller degree than our p, what we divided by. That was what that definition was trying to tell us at the bottom. If our remainder does not have a smaller degree, then something went wrong. Or you stopped too soon. So long division is long and kind of annoying. But we can do long division when we have things that we're dividing by that aren't necessarily factors or roots. So in this case, we had x squared minus 3. So that one we could not find like factor roots to be able to use something like synthetic division. I would say synthetic division only works when we have those real roots. So something like this, we have irrational roots because we'd have square root of 3. Positive and negative square root of 3. Doing that in synthetic division would be obnoxious and gross and ew. So when we have irrational roots, we're going to have to use long division. But if we have rational roots, we're going to use something called the remainder theorem, which is up here, that says if f of x, our function, is divided by x of f, x minus c, then the remainder is f of c. So for our synthetic division, we use the root. The remainder is not 3. So what it's saying is that we can find f of 3 using something like synthetic division, because sometimes these functions get super gross. So what we can do is I can find f of c. So we're going to find f of our c here. What's our c? X minus 3. What's c? 3. So we're going to find f of 3. We're actually going to find it both ways here so we can see what this is saying and why we care. Because especially when we couldn't use calculators on this, some of these things would get super gross. What if I had x to the 7th? Ew. So we're going to use synthetic division for this. Synthetic division is when we use just our coefficients, not skipping any from our function. So what is our coefficient for our x cubed? 1. What's our coefficient for our x squareds? What's our coefficient for our x's? X's? 0. We cannot skip x because it's not there. We have to use every term. How about our constant? -5. When we use our roots, the number we put outside, that's going to be that c. The same thing we did when we were finding f of c, when we figured that 3 out. That's going to be the piece we divide by here. So, just as a reminder, like, do you remember how to set up the synthetic division? Questions on the setting up part? I know it's been a while since we did synthetic. Okay. Oop, it's gonna blink. So when we do our synthetic division, first term drops. We take this piece times this piece. We're gonna have our 3 times 1. And it goes here. 3 times 1 gives me 3. And then the benefit in synthetic division, instead of having sign issues that we worry about, we add. So we're not subtracting things, we add things. So -4 plus 3 is -1. Bottom times the left and put it under. -1 times 3 is -3. And then we add. 0 plus -3 is -3. Bottom times the left and put it under. -3 times 3 is -9. And then we add. -14. What's up? We're going to do that too. Because hypothetically, theoretically, we should have the exact same answer. But the only problem with that is when we don't have calculators or things don't work. If I had x to the 7th and we had maybe f of 12, those numbers get real big real fast. So what our remainder theorem tells us is that this remainder right here should be the exact same value as f of 3. Should be the same as this remainder. And that's what we're going to check, yeah. And our quotient, the thing that we can have, is actually going to be this remainder function down here, which always has 1 degree less than what we started with. So this would be 1x degree smaller, so 2x squared, minus 1x minus 3. This would be our quotient, our q of x. So we can use it still to do the same things as long division. I'm getting the same pieces. I've got my remainder of -14. I've got my quotient of 1x squared minus 1x minus 3. And just to double check and see that this is right, we're going to find f of 3 the traditional way, where I take my 3 and substitute it in place of the x, 3 cubed, minus 4 times 3 squared, minus 5. I'm almost out of space. Well, we can do this one. This one's not awful. 3 cubed, that's going to be 27. 4 times 3 squared, 4 times 9, that's 36, minus 5. So we see we can get, even if we do it the traditional way, our f of 3 equals negative 14. The benefit of having this as the remainder theorem, again, is if we have really big numbers or really big exponents or lots of pieces, or if I'm doing it repeatedly over and over and over again, the synthetic division is honestly sometimes faster. Okay, questions on this one? We're going to practice this again, and in fact, we're going to use the same function for the next one again, just so we can practice it. But we're going to be using this remainder theorem for this part. Okay. So we're going to find the remainder if that same function, this is the same one we just had, is divided by x plus 2. So what is our c going to be? Negative 2. Because remember, this was x minus c. We use our root, not the factor. The root is negative 2. So when we set this up as synthetic division, we're going to use our negative 2 over here. And then we use our coefficients, not skipping any, and going down. So my 1x cubed, negative 4x squared, 0 x's, minus 5. So drop, multiply, and put it under. So the first term drops, 1. 1 times negative 2 goes under here. We got negative 2. And then we add negative 4 plus negative 2. We get negative 6. Because we add these together. Negative 6 times negative 2 gives me positive 12. And then we add. 0 plus 12 gives me positive 12. 12 times negative 2 gives us negative 24. And we add those together. What's our remainder going to be? Negative 29. So f of negative 2 equals negative 29. This last term is our remainder. So our quotient, if we divided them, because sometimes they'll ask us for the quotient, so it's good for us to mark that down too. Our quotient would be what? If I was to do this long division, what would we wind up with at the top? X squared minus, let's see, switching that, minus 6x plus 12. This gives us our quotient. The last term is what's going to be our remainder. Which is also the value of that function evaluated at that value. So it has lots of pieces that all mean the same thing. Okay. Questions on this one? What's up? You could. We're not gonna. You don't need to, but you can if you want to. But when we have x values, especially that are negative, sometimes that throws us off sign-wise when we do things like this. So it's just another way to kind of get that information where we need it to be. So now we're going to do another set. So I've got the same function, and I want to find the remainder if f of x is divided by each of these. So we're going to set up our synthetic division. I'm going to start with this one. What are my numbers that are going to go across the top? One, -1, 2, -4, -8. And what's going to go outside on this one over here? A -3. So our root happens at -3. That's where we're getting that information. So we're going to drop, multiply, and put it under. So we drop the 1. 1 times -3 is -3. And then we add. -1 plus -3 is -4. Bottom times the left and put it under. -4 times -3 is +12. And then we add. Two plus 12 gives me 14. (14) times -3 -42. So we add them together, and we get -46. And -46 times 3. Thank you. Nah, not negative. -46 times -3 gives me positive. And then we add them together. We get 130 as our remainder. So our f of -3 is 130. What would our quotient be here? How would we write q of x? Yeah, we'd have our, it's 1 degree less, so it's going to be an x cubed minus 4x squared plus 14x minus 46. So we could find that quotient. Like, we can do that. Those coefficients are coming from right here. All right, let's do the next one. It's the same function. So when we set this up, I'm going to use those same coefficients. I'm going to make it smaller. 1, -1, 2, good. -4, -8. What goes outside? -1. So do it. You can do this. You've done these before. So -1. and 0. So what's our remainder? What does that mean? It goes in there evenly. It's a factor. X plus 1 is a factor of this polynomial. X plus 1 is a factor. So what we have left over, q of x, is what? X cubed minus 2x squared plus 4x minus 8. If I took that times my x plus 1, I would get exactly my original f of x back. Those two things are factors. They make up our f of x. And in fact, what we're going to be doing, and honestly for a lot of the rest of this chapter, is using this because we're going to be factoring these kinds of polynomials so that we'll be able to graph them properly by the end. So if our remainder is 0, that means it's a factor. Which directly ties us into our last theorem, which is what we're going to use on Monday. I'm going to give you the theorem so that we have plenty of time to write it down. And then you guys, if you guys have any questions on stuff, we'll have some time to do that. So I'm going to give you our factor theorem. This is what we're going to start with on Monday. And we're going to be taking these polynomials and using this to see if we can try and get everything down into factored form. Or what we need to do to factor. So we're going to focus on using this factor theorem on Monday quite a bit. Okay? So you guys can finish out homework 1. We've done everything on homework 1. And you guys can get started on homework 2. I'll put the numbers up here in a minute. But yeah. There were a couple of questions on homework 1 that were, I'm sorry, genuinely awful. 35 and 43 in particular. That's called IU picked them and I didn't get a chance to write them, so skip them.
Which one?
The last two.
35 and 43.
The last two.
Okay.
Because they are genuinely terrible.
Thank you so much.
So skip them. I intended for it to be 37, but I mistyped it. So, and I didn't catch that anytime you guys were in here. I didn't catch it until 4th period yesterday. So I switched it for them. But I didn't catch it in time for you guys. Oh, sorry. That one. So here's 4.2. Hopefully this weekend I'll get, things keyed up so that I know for sure that our questions are not super gross. But that's called IU gave us actual questions that they want us to use, and I'm using them, but I didn't get a chance to write my answer keys yet. That's 4.2, not 4.1. This is the next one, which you guys, at this point, you could do everything up through...
Oh, yeah, we do have the PSA.
We've done things up through 11, but you could probably figure out up through 17. We've talked about it, and we've kind of done it. But you could probably do it. What's up? On 4.1. Let me look at 15 real quick, because I don't remember. That's where you're going to factor out that fraction and then use your sum or difference of cubes. The sum or difference of cubes thing, we did it yesterday. Hang on, let me pull it up real quick.